Hello, everybody. This is my lecture for week 11, session 3. So we already discussed chapter 6. In chapter 6, you learned three main topics. We discussed the second law of thermodynamics. Also, you learn about the refrigerator cycle, heat pump and heat engines, and then eventually we discuss the Carnot cycle. So if you remember, for the heat engine, actually you have two options to determine the thermal efficiency of heat engines. For a reversible process, you can use actually either this equation or the general definition for thermal efficiency. The general definition for thermal efficiency is the desired output over required input. For you learn for heat engine, the desired output is W net or W out, and then the actually required input is QH. So you can either use this equation or the general definition for thermal efficiency to find the thermal efficiency of a reversible process. For the reversible process or Carnot heat engines, you can use the same actually equation to find the thermal efficiency. However, here you need to have the QL over QH for the reversible process. Keep in your mind that, guys, in most cases we don't have the QL over QH for the reversible process, or you may have it, but in most cases we don't have it. So normally we use the second equation, TL over 1 minus TL over TH, to find the thermal efficiency of a reversible heat engine. Keep in your mind that the temperature must be absolute temperature. And then for the COP of refrigerator and heat pump, again, for the irreversible process and reversible refrigerator or heat pump, you have actually different equations to calculate the COP and for refrigerator and heat pump. Let's solve one more example from this chapter, and then we can start chapter 7. So here we have an air conditioner, and then the working fluid is refrigerant 134A. And so we know the temperature for the room is 23, and then the outdoor temperature is 34. And so we have some information for the heat actually gained through the law, and also heat generated by the computer and some other appliance. Then you have some information for the actually property of refrigerant enter the compressor and then leave the compressor, and then you ask to calculate the COP, the maximum COP, and also the minimum volumetric flow rate of refrigerant. So please open the handout that I share on the blackboard, and yeah, here you can see the handout. So as a first step, this is the unknown prompter. As a first step, I already mentioned in my previous lecture, it's a good idea if you draw a simple actual schematic of the process. So I didn't show the schematic of this process. I just want to make sure that you guys, can just draw a simple schematic for this problem, and also, for the other problem in this chapter. So the first step, I actually explain you guys, in this chapter 7 and chapter 9, normally we are dealing with the cycles. And then in the cycles, normally we have more than one equipment. So it's a good idea if you draw a schematic for actually cycle, and then make a decision based on the available information. So please pause this video and then spend 5 minutes, and then just draw a simple schematic for this actually process. Okay, so the second step, you need to just transfer all available information to the process schematic. So before you transfer this, information, let me show my actually schematic. So yeah, look, guys, here you can see actually we have the refrigerator, and this refrigerator actually work between two reservoir, and then you have the temperature for the sink and the temperature for the source. So then we have some information for the compressor. You know that each refrigerator has four equipment: evaporator, compressor, condenser, and the expansion valve. So I just on the left side you can see the actually the general schematic for the process, and then on the right side you can see the refrigeration cycle. Now please spend 2 minutes and then just transfer all available information to this schematic. Okay, so look guys, we have both temperature for the reservoir. So we know that the room temperature is I think 20, let's see, yeah, 23, and then the outdoor temperature is 34. Keep in your mind that you must convert this temperature to the absolute temperature, because if you want to calculate the COP for the um, Carnot cycle or reversible refrigerator, you need to use the absolute temperatures. This is the first one. Also, we have some information for the compressor part, correct? You know that the actually fluid enter to this compressor at 400 kilopascal and it's saturated vapor, and then leaves this compressor at 1200 kilopascal and 70 degrees centigrade. Also, you have the volumetric flow rate, and then this is actually cycle. So this volumetric flow rate is sorry, not the volumetric flow rate. The mass flow rate is constant, but not the volumetric flow rate. So you have the volumetric flow rate inlet to this, compressor. This is actually the V.1. Okay, so question, guys. We have some other information, in the, actually, a statement, question statement. So please spend 2 minutes. What do you think about this, actually heat gain through the windows, and also this heat generated by the, appliance? What do you think? What is this, to actually values, for the, these two actually, hits? Okay, so look, guys, um, if you assume that the temperature of this room is constant or there is a steady state condition, then what happened? All heat generated in this room and also heat gain, from the windows actually must be rejected to the, actually, refri to the refrigerator cycle. So meaning that if you just add the heat gain by the windows and also heat generated by the appliance, you can calculate the Q dot L. So the combination of these two actually term is the Q dot L. So we can calculate the Q dot L. This is all available information, guys. So you just transfer, first step, you just draw a simple schematic. Now you transfer all information. Now you're ready to solve, the first part. For the first part, you are asked to calculate the, COP, the actual COP. The actual COP is, the COP for, irreversible, process. So, please spend, this is a step three, please spend 2 minutes and then list all available equations, all equations that you can use to find the actual COP or the COP for the irreversible cycle. Please pause this video, spend 2 minutes, and then list all equation that you can use to find the COP, the actual COP. Okay, so let's go back to my guided note. Uh, so yeah, for the COP of irreversible, refrigerator, you can use one of these two, equations. So this is based on, the general definition of the COP, the desired output, which is the Q dot L over the V dot in, and then this is, based on if you substitute for the W dot in, from the, from the actually energy balance for the cycle, you can draw this, derive this, equation. So you can use one of these two equations and then question. please spend 2 minutes and then answer which equation is the best one to find, the COP, the irreversible COP for this refrigerator. Please pause this video and then just answer this question. Okay, look guys, for this problem, you can use both these two equations. You can use either equation 1 or equation 2 to find the, COP for irreversible refrigerator. So you can use either the first one and second one. So I picked the first one, to just solve this problem. It's up to you. You can just pick, the first one or the second one. Now, to find the COP from the first, equation, if you want to use the first equation, yeah. So this is the first equation. Look guys, you find the COP, you need to have the Q dot L. You already determined the Q dot L, so you need to find the W dot in. Please pause this video and spend 5 minutes and then find a method to actually, to calculate W dot in. Or go ahead and calculate, the W. What do you think? What's the best actually, method to calculate the W dot in? Please pause this video and then try to calculate W dot in. So look guys, to find the W dot in, so what you need to do, you need to actually write the energy balance for the compressor. So look, if you just draw that, schematic, this schematic, this is really helpful, to just make a decision. So you need to calculate W dot in. So you need to write the energy balance for the compressor. So if you write the first thermodynamic law for this compressor, look guys, we don't have any information for, Q dot net. Please just spend 2 minutes and then try to simplify this equation. We discussed it, later. So please pause this video and spend 2 minutes and then try to simplify this equation to find the W dot net. Okay, look guys, we don't have any information for the for the Q dot net. So you can assume that, this is actually a adiabatic, compressor, and then we can cancel the W dot net. So you can cancel the velocities and also, the elevation difference, and then based on, this available information, you can write W dot in equals to the M dot H2 minus H1. So to calculate the W dot in, what you need to do, you need to find enthalpy for the fluid into the compressor, the exit, enthalpy, and also M dot. So please spend 5 minutes. You have, some actually, two intensive property for both state 1 and state 2. Go ahead, use the tables or other methods to find H1, H2, and also M dot for this case. Please pause this video, spend 5 minutes, and then find, these three unknown parameters. Okay, to find the H1 and H2, I'm sorry, I use the table A12. Thermophysical properties for saturated refrigerant 134. This is a pressure table. So for the first state, for the fluid enter to the compressor, we know that the pressure is 400 kilopascal, and then this is the saturated vapor. So you can report the Hg and also nu G as thermophysical properties of this fluid. So for the second one, we just know the pressure and temperature. We know that the fluid leaves the actually compressor has a pressure of 1200 kilopascal and a temperature of 70 centigrade. So before you make a decision, guys, you need actually to find the state of this fluid. So we have the pressure. At this pressure 1200, the saturated temperature is 46.29, and then the given temperature is 70. So the given temperature is higher than the Tsat, meaning that the fluid, this fluid is actually superheated fluid. Correct? So because this is the superheated fluid, you need to use the superheated table for refrigerant 134A to find the H enthalpy, actually H2. So I just use the table, and then the H2 is 300.63 kilojoule per kilogram. Now you have the H1, H2, you have the new, and then you can find, also you have the volumetric flow rate, you can find the M dot. So simply the M dot is volumetric flow rate 1, you have the volumetric flow rate over the new one. What you need to do, you need to convert the 80 liter per minute to cubic meter per second. And then you can find the M dot. If you substitute H1, H2, and M dot into this equation, you can find the W dot in. Okay, now you have the W dot in, and then simply find, the COP. You can simply find the COP. If you substitute in the equation for the COP, you have the Q dot L, W dot in. The COP will be 4.33. So this is the first part, part one. So you just determine the COP. Now, the COP max, the second part, we need to find the COP max. So, if you remember, guys, the COP max is actually for reversible, refrigerator, or for Carnot, refrigerator. So what you need to do, guys, you need to just write equations for the COP max. Just list the equation for the COP max, and then based on the available information, make a decision which equation do you prefer to find a COP, and then find the COP max based on that equation. Please pause this video, spend 2 minutes, and then try to calculate the COP max. Okay, so for the COP max, look, guys, you have the TL and TH, so you can simply use this correlation to find the COP max, 1 over TH or TL. Just keep in your mind that you need to use the, absolute temperature. So the COP max is 26.91. For part 3, you are asked to find the minimum volume flow rate at the compressor inlet. You already determined the volumetric flow rate, but that volumetric flow rate, actually you have the volumetric flow rate, but that volumetric flow rate is not the minimum one. So look, guys, you are able to calculate the M dot. How? Let's go here. Yeah, look, but by using this actually, energy balance equation, you can calculate the M dot. So to calculate the volumetric flow, the minimum volumetric flow rate in the inlet, you need to calculate the minimum actually mass flow rate. And if you multiply this minimum mass flow rate by the sorry, a specific volume, you can calculate the minimum volumetric flow rate. So to calculate the minimum volumetric flow rate, if you rewrite, that energy balance equation for the compressor, you can write the W dot in mean equals to the M dot mean times H2 minus H1. So to calculate the minimum mass flow rate, you need to have the minimum work, correct? To calculate the minimum work, let's check, the equation for the COP. So the COP is Q dot L over W dot in. If you just substitute the W dot in mean in this equation, this COP will be the COP max at constant Q dot L. So to calculate the W dot mean, you need to use the COP max. So if you use the COP max, you can calculate the W dot mean. By using the W dot mean, you can calculate the M dot mean. By using this M dot mean, you can calculate the minimum volumetric flow rate. Please pause this video and then spend 3 minutes to calculate the minimum volumetric flow rate. Okay. So here, did minimum work, and then minimum mass flow rate, and then minimum volumetric flow rate, based on, the available information, which is 12.9 liter per minute. Please study examples 6.1 through 6.7. from your textbook, and then this is chapter sorry 6, and let's start chapter 7, entropy. In chapter 7, we are working on, actually, we work on four different, topics, four main topics. The first topic is entropy. We discussed the, basic concept of entropy. What is the entropy, and then, what's the origin for the entropy? What's the definition for the entropy? What's the S generation? And, these things. Keeping in mind that, guys, you already saw the entropy. If you just check the reference tables, for example, this is the table A12 for the saturated refrigerant that I used a couple of minutes ago for to solve that problem. So look, guys, the last part is for the S. This is for the entropy. So you already saw the entropy. In this chapter, actually, we go over the concept of entropy. We discuss those concepts. This is the first one. Actually, we'll go over this part today. Then we just learn different methods to calculate the entropy changes. Remember, when we define the internal energy, when you learn, the enthalpy, then I explain you guys that for the, process, for the engineering process, you need to calculate the delta U, delta H. So here we are interested in the delta S. So you will learn different methods to calculate the delta S. You will learn two actually methods to calculate the entropy changes today, and then we'll learn some more methods in the next lectures. Then we will discuss about the isentropic process. You will see that isentropic process are the process with constant S, and adiabatic process, or internally, sorry, they are the constant S, or they are internally reversible and adiabatic process. And eventually we will discuss the isentropic efficiency for some actually steady flow devices such as pump, compressors, and turbines. So these are four main topics of this chapter: entropy, entropy changes, isentropic process, and isentropic efficiencies for various steady flow devices. Okay, let's start the first part, the entropy. So based on the second thermodynamic laws, we can actually define the Clausius inequality. So the Clausius, based on the Clausius inequality, the delta Q over T for each and every cycle is always equals or lower than 0. This inequality is valid for all cycles, for reversible, irreversible, or irreversible one. And we can actually prove this inequality. Here you can see how we can prove this inequality. Assume that we have a thermal reservoir with a temperature of TR, and then there is a reversible cyclic devices. And these reversible cyclic devices get delta QR from this thermal reservoir, and then produce the delta W reversible. And then this actually cycle reject delta Q to the to another system. This is a cylinder and piston, and then this cylinder and piston gain this delta Q, and then due to the expansion, due to of the boundary work, this system produce actually generate delta W system. So if you just write the first thermodynamic law for this control volume, for this control volume here, we can write E dot in minus E dot out, or E in minus E out equals the DE for the system. What is the E into this system? The E into this system is delta QR. What is the E out from this control volume? Is the delta W reversible and delta W for the system. If you combine these two, actually delta W, and we just combine these two delta W, and we just show them as the delta WC. Now let's combine these three equations. If you substitute for the E dot in from this equation, E dot out from this equation, we can rewrite these three equations into this format, correct? So this device is a reversible cyclic device. So meaning that we can write for this, device, we can write delta Q R over delta Q equals to the TR over T. You learned it, in chapter 6, if you remember, correct? And then from here, you can calculate the delta QR. So if you substitute for delta QR from this equation to this one, we can write delta WC equals the TR delta Q over T minus DE for the system. Let's actually get integral, from this equation. If you get integral from this equation for a cycle, so this term will be WC, this term, the TR is constant, you can bring it out from the integral, and then you can write the integral for a cycle, delta Q over T, and then this term will be 0 because this is a point parameter. We already discussed, the point parameter in chapter 2, and then or chapter 1, I think. And then you saw that, actually for each and every cycle, the integral or the delta for the point parameter is 0. So from here you can write the WC equals to this term. Now let's look at this, actually system. If you look at this system, there is actually, this system is exchanging heat with one reservoir, correct? So, and this is not, actually valid based on, the second thermodynamic law. So because this system is actually exchanging heat with one, actually, reservoir, this WC must be negative. It's impossible to produce, W.net for a, system that just exchanging heat with one reservoir. You just remember, this explanation from chapter 6. So what happened? This term must be negative. If this term is negative, so the right side must be negative. Let's look at the right side. The right side, TR, is always positive. So if this term is negative, this term must be either negative, also it can be, 0. So this term must be either negative or 0. And then this is actually, the Clausius inequality. Keep in your mind that this actually inequality is valid for both reversible and irreversible processes. For reversible processes, this term equals to 0, and for the irreversible processes, this term is less than 0. Correct? So now what happened? The Clausius found that, actually he found a new, he found that he's dealing with a new thermodynamic, property, and then he named this new property as entropy. So what is the entropy? Entropy is, we just use the actually S to show the entropy, and then ds equals the delta Q over T for the internally reversible processes. For irreversible processes, you saw that this term is actually lower than 0. Now, keep in your mind that entropy is an extensive property. Why things, extensive property? Because, it's integral, for actually reversible process for a cycle equals to 0. So it's an extensive one. What's the unit for the, actually entropy? The unit for the entropy is, Q is kilojoule, and then for the temperature is, Kelvin. So the unit for the S entropy is kilojoule per Kelvin. We can define the entropy per unit mass. We can divide entropy by the M, and then we can define entropy per unit mass, or lowercase s, and then the lowercase s is an intensive property. If you remember from chapter 2, if you divide an extensive property by mass, the product is an intensive property. And then the unit for lowercase s, or entropy per unit mass, is kilojoule per kilogram Kelvin. So what is the entropy change, guys? I told you we are actually interested in, to calculate the delta S. So the delta S is, you saw that actually S is a, point parameter. You can write the delta S is S2 minus S1, and then this term equals to the, integral from 1 to 2 for the delta Q over T. So to calculate the delta S, you have actually two options. So If you have a relationship between, Q and T, you can use this integral to calculate the delta S. This is the first method. But in most cases, you don't have actually this relationship between Q and T. The second method, you can use actually the tables. If you have the tables, the property tables, you can just find the S2 and S1, and then you can find the delta S. So today you learn two different methods to calculate the delta S. The first one from actually this equation for the internally reversible process. So for internally reversible process, if you have the relationship between Q and T, you can substitute into this, integral, and then you can calculate the integral to calculate the delta S. The second method, if you have the actually property tables, you can find the S1 and S2, and then you can find the delta S. Keep in your mind that we need to learn some other methods to calculate the delta S. Why? Because in previous chapters you saw that we just have the table of properties for few, substances. So in next, lectures, you will learn some other methods to calculate, the delta S. But in this actually step, you just need to know these two different methods. Let's go over this method, guys. To see, what happens if you have, relationship between Q and T. The actually easiest method, the simplest, method to have a relationship between Q and T is internally reversible isothermal heat transfer processes. For this type of process, temperature is constant, and then you can simply solve, that equation. Look, the delta S, because this is an internally reversible process, you can write delta S equals to the integral from 1 to 2 delta Q over T. Again, this equation is just valid, this part, for for reversible processes. So for this actually process, it's internally reversible, so you can write this equation, and then this is an isothermal one, so the temperature is constant. And then you can bring the temperature out, and then this integral will be Q, and then you can write delta S equals to Q over T naught. This equation is valid for internally reversible isothermal heat transfer processes. As an example, if you remember, actually you can use this equation to calculate the delta S for thermal energy reservoirs. Remember when I defined the reservoir, I mentioned that the temperature of those reservoirs are constant. So, and then you can use this actually equation to calculate the entropy changes of thermal energy reservoir. So keep in your mind that Q can be positive or negative, and then because the Q can be positive or negative, this delta S can be either positive or negative. Okay, now the increase of entropy principles. Let's assume that we have actually a cycle, and then from step 1 to step 2 there is either reversible or irreversible process, and then from step 2 to step 1 there is an internally reversible process. If you write the Clausius inequality, this inequality is valid for all both reversible and irreversible processes. This delta Q over T, we can write this is the combination of the delta Q over T for the first actually process and for the second process, correct? So for the second process, because this is an internally reversible process, you can write the delta Q over T, the integral of actually this and the integral of delta Q over T equals to the delta S, or S2 minus S1. If you combine these three equations, and then you substitute, for this term from the third equation, you can actually write this, equation. Now, if you bring this term to the right side, then we can write S2 minus S1 is higher or equals to this, term, correct? So, or in the differential form, we can write the ds is always greater or equal to the delta Q over T. Now, uh, look guys, we can actually convert this delta Q to the delta this inequality to the equality. How? uh, if we just add a term for the S generation, look, based on this always the ds is higher than delta Q over T, meaning that we have always entropy generation in the system, correct? So if we add the entropy generation into this actually equation, we can just convert it to the equality. So here you can see, guys, look, if we add the S generation, then we can convert this inequality to the equality. So based on this equation, guys, the S generation is always positive or equals to 0, correct? In the previous slide you learned that the delta S can be either negative, positive, or 0, correct? The delta S for the system. So the delta S for the system can be either negative, positive, or 0. However, the S generation is always positive or 0, correct? Based on this actually equation, we convert it to the generation. I just forgot to mention that, guys. Entropy is actually the energy, actually the loss of energy available to do work, correct? It's actually an indicator for the energy loss. So yeah, we lost energy, correct? When you just want to do some actually I mean energy available to do work. So again, guys, keep in your mind that the delta S can be either negative for the system, positive or 0. However, the S generation is always positive or 0. For example, for an isolated system. What is the isolated system? Isolated is an adiabatic closed system. For isolated system, this inequality, if you write this inequality, it's an adiabatic process. So the delta Q is 0, correct? So from here you can see that the delta S for isolated system is always greater or equals to 0. The entropy of an isolated system, the delta S. So, and isolated system normally is a combination of several subsystems. For example, you can just consider the universe as a an isolated system. So here, what's the S generation, guys? The S generation is the combination of the delta S for the system and surrounding. And then here you can see, guys, that the S generation is always positive or, equals to 0 for, an isolated system, meaning that the entropy of the universe is increasing, actually continuously increasing. So based on this equation, the S generation or the total enthalpy of the universe, which is an isolated system, is continuously increasing. Okay, guys. So here you can see, actually it's a kind of, summary. The S generation, keep in your mind that the S generation is a combination of the delta S for the system and the delta S for the surrounding. And then the delta S, for the system can be determined, from this, equation. The delta S can be either negative, positive, or, 0. However, the S generation is always positive or equals to 0. So based on the S generation, you can make a decision, what kind of actually process do you have. So if the S generation is positive, there is an irreversible process. If the S generation equals to 0, you have reversible process. And then if the S generation is lower than 0 or negative, it's impossible to have this kind of, process. So here are some remarks about the entropy. So in chapter 6, you saw that actually the second thermodynamic law define the direction for each and every process, meaning that processes can occur in a certain direction but not in any direction. So here you can see actually another definition, for the second thermodynamic law. You saw that the S generation must be always, higher than zero or equals to zero. So we can mention that processes occurs, in the actually, this direction, to have S generation always higher than zero or equals to zero. So process that violate this principle is impossible, correct? You just learned another, statement for the second thermodynamic law. Keep in your mind that the entropies and non-conserved properties. What does that mean? For example, for the mass, you write, the mass conservation equation, correct? M dot in minus M dot out equals the dm, over dt for the system. But entropy, you saw that the entropy increases, for the actually, uh, the S generation increases. So meaning that, we don't have actually, entropy conservation equation the same as, energy, conservation equation. And then the third one is, entropy generation is a measure of the magnitude of the irreversibilities, correct? The higher, actually, entropy generation means, more irreversibilities. So entropy change of pure substances, we learned actually two different methods. The first one, to calculate the entropy change was, for if you have a relationship between Q and T, and then for a specific case, if we have isothermal reversible process for, let's say, for, thermal reservoir, you can calculate the delta S, you can write delta S equals to the Q over T naught. The second method is, from the tables. If you have the table, you can simply calculate the delta S. How? You can use the same concept, the same equation that you already used to calculate delta H and, H and, U in chapter 2, 3, 4, and 5. Look, guys, for example, if you have a compressed liquid, enthalpy equals to the S for the saturated liquid at given temperature. If you have a saturated liquid vapor mixture, then enthalpy equals to the SF, S for saturated liquid, plus X quality times S, F, G. And then if you have a superheated table, we can use, the enthalpy, the actually superheated tables, to find the delta S. Keeping in mind that in the tables you have the lowercase s, you have the enthalpy per unit mass, so you need to multiply the delta S by M to calculate, the total delta S. Also, you can plot, the TS or PS diagram, and then you have this, dome, and then, those, constant pressure and temperature, lines. Okay. So the last part of this, lecture is isentropic processes. Isentropic processes is actually are processes with delta S equals to 0. If S1 equals to the S2, you are dealing, with isentropic process. So delta S is 0 or S remains constant. This is a TS diagram, for the isentropic process. Keep in your mind that S1 equals to the S2 when we have internally reversible process and adiabatic one. So if you have a process which is internally reversible and adiabatic, you can write S1 equals to the S2 or delta S equals to 0. This is very important. We use, this actually point to solve problems. Keep in your mind that if you have internally reversible and adiabatic process, you can simply write S1 equals to the S2. Here is the summary, guys. We learned the Clausius inequality. Then you learn two different methods. You just saw that, for the internally reversible process, you can write the delta S equals to, this equation. And then if you have a relationship between delta Q and T, you can calculate the delta S for internally reversible process by using this correlation. So for internally reversible isothermal heat transfer processes, you saw that this delta S, by using this, equation, you can write the delta S equals to the Q over T naught. And then if you have the table of properties, you can use the table of properties to calculate the delta S. What is the entropy? Entropy is actually, Clausius, just found this, property, and then simply entropy is the loss of energy available to do work. It's an indicator that shows, irreversibilities, in the process. So keep in your mind that, guys, the delta S for a system, can be determined, for actually both for irreversible process from this correlation. Let's go back here. Look, guys, this equation, again, this equation is valid, for internally reversible processes. For irreversible processes, you can use, this correlation, again, this integral plus S generation. Correct. So this one is valid for internally reversible, and this correlation is valid for irreversible, processes. So the entropy change, the delta S of system can be negative, positive, or zero. But S generation is always positive. Keep in your mind, positive or zero. So the S generation, keep in your mind, that is a combination of the delta S for the system and surrounding. So we need to calculate both delta S for the system and surrounding to calculate the S generation. And then the entropy change can be, yeah, we just discussed this one. So this is the summary, for this, lecture. Next lecture, I will solve, some problem, and then we can just go over, the main part of this, chapter. Have a great day, and thank you so much.